Earth's atmosphere is divided up into layers based upon how the temperature varies in each layer. And there are two factors that are going to affect the temperature. One is density. And the symbol we're going to use for density is a Greek letter rho, kind of a curly P. And the rule of thumb is that as the density decreases, the temperature decreases. Because as air density gets lower, its ability to hold heat decreases. And if that's all there were to our atmosphere, then the higher up you go, the lower the density, the lower the temperature. However, there is a second factor that affects air temperature, and that is light absorption. In certain layers of our atmosphere, different wavelengths of light get absorbed. And when light is absorbed, temperature increases. So for each layer, it's going to be a matter of which of these two effects is the dominant effect. Density is going to continue to decrease as you go higher and higher, but light absorption may or may not occur. And so if you have light absorption, then you are going to get warmer in that layer. So let's look at each layer and see what's happening. The first layer, the lowest layer, is the troposphere. And this layer is going to be where weather occurs. So that's where our cloud formations occur. And of course, being the layer closest to Earth, this is where we are. We are in the troposphere. And the troposphere temperature profile is going to be dominated by density. So in the troposphere, the density is going to decrease as you go higher. So the temperature is going to decrease as you go higher. And in the illustration here, it shows a little mountain. And so, all our mountains, even the highest mountains, are within the troposphere. And as you know, if you're going to go climbing the tallest mountains, the higher up you go, the colder it gets. And the higher up you go, the more likely you are going to need oxygen. And that is because of the decreasing density. When somebody says the air is getting thin, what they mean is the density of the air is decreasing. So the troposphere is going to be characterized by these factors. So that's the troposphere. The next layer above the troposphere is the stratosphere. And in the illustration here, this is, as you can see, where high altitude jets would be found. Now in the stratosphere, we still have the effect that the density is decreasing as we travel higher and higher. That's true for every layer. But the stratosphere is also home to the ozone layer. And ozone absorbs ultraviolet light. So even though our density is decreasing, we are absorbing light. And because of that, the temperature is going to increase as you go higher up in the stratosphere. Because the topmost part of the stratosphere is where the ozone is most concentrated, and that's where most of the ultraviolet light gets absorbed. So that's going to be the hottest part of the stratosphere. And as you travel down through the stratosphere, less and less ozone, or less and less ozone, and less ultraviolet is being absorbed. And so it gets cooler as you go down rather than warmer. So that is our stratosphere. The next layer above the stratosphere is the mesosphere. And it's kind of hard to tell on this illustration, but that's a meteor. So the mesosphere is where we see those streaks of light that we call meteors, which are little pieces of rock that are falling through our atmosphere and burning up. Now the mesosphere returns to the same trend we saw with the troposphere. As you travel higher, the density decreases, and there is no absorption of light, so the temperature decreases as well. So the mesosphere is very much like the troposphere in terms of how the temperature behaves with altitude. The last layer on here is labeled both exosphere and thermosphere. You will also see it called Ionosphere. So all of these terms refer to the outermost part of our atmosphere. And this is where essentially the space station is when it's orbiting the Earth. Any kind of spacecraft in orbit around the Earth. Now satellites tend to be higher up, but manned space exploration in orbit around Earth tends to be in the ionosphere, or the outer part of the exosphere. And as the name ionosphere implies, this part of our atmosphere is ionized. And that means that the atoms have lost an electron, which gives this part of our atmosphere a charge. And that charge actually allows ham radio operators to bounce signals off of the ionosphere. It's also why sometimes late at night, if you listen to AM radio, you can pick up stations that are many hundreds to thousands of miles away. It's the signals bouncing off of this ionized part of our atmosphere. Now the density here is incredibly low, so our density is still decreasing. But what's making it ionized is that this part of our atmosphere is absorbing high energy light, in particular X-rays and gamma rays. And I'm going to use the Greek symbol for gamma. So this is gamma, that kind of ribbon-looking symbol. So these are the two shortest wavelengths of light. That's the highest energy form of light. And this is a good thing because these things would kill us if they came through our atmosphere. So our upper atmosphere is protecting us from these very deadly forms of radiation. And because it is absorbing light, the temperature is going to be increasing as you go up in through the ionosphere up to the exosphere. So that is our uppermost level of the atmosphere. And as you see, we have this general trend with the temperature. As you go higher in the troposphere, temperature gets cooler, then it gets warmer through the stratosphere, then cooler through the mesosphere, and then warmer once again as you go up through the ionosphere. Now, word of caution about the temperatures here. When you get up into the ionosphere, even though the temperature is going to have numerically high values, this low density means that as far as your skin is concerned, it's still going to feel cold. Temperature is actually a measure of how fast the atoms move. Now, at ground level, there's a lot of atoms in our atmosphere. So a lot of fast-moving atoms, that's going to translate that energy to your skin. It's going to feel warm. But up in the outer part of our atmosphere, the density is so low, the atoms are so spread out, even though they are moving around quickly, there are so few of them that as far as your skin is concerned, it's still going to feel insanely cold. So there's a difference between the numerical value for the temperature and how your skin reacts to that temperature. But that is our atmosphere layers.